Hello everyone, we present SteerNeRF, accelerating NeRF rendering via smooth viewpoint trajectory. We provide a new perspective on NeRF rendering acceleration. We propose to fully leverage the critical fact that the viewpoint trajectory is usually continuous and smooth in interactive applications. We exploit smooth viewpoint trajectory to accelerate NeRF rendering, achieved by performing volume rendering at a low resolution and recovering the target image guided by multiple viewpoints. Our method, dubbed SteerNeRF, enables fast rendering with a low memory footprint. Exploiting available rendered information from the neighbor viewpoints, we reduce the 3D sample queries in raymarching to speed up rendering and cooperate with an efficient neural renderer to preserve visual fidelity. Many works have focused on elevating the rendering speed of NeRF, yet there is a trade-off between rendering speed and memory cost. State-of-the-art acceleration approaches substantially increase rendering efficiency at the expense of large memory consumption. For example, by pre-caching the intermediate output of the MLP or using discretized voxel-based representations, leading to hundreds of megabytes to represent a single scene. While there are some attempts to accelerate NeRF rendering with a low memory footprint, like adaptive sampling methods, the rendering efficiency is still not on par with cache-based methods. In practice, it is desired to achieve faster rendering at a low memory cost. How can we push the frontier of the efficiency memory trade-off? Orthogonal to existing methods, we provide a new perspective on NeRF rendering acceleration to push the frontier of the trade-off between rendering speed and memory cost. We propose to fully leverage the critical fact that the viewpoint trajectory is usually continuous and smooth in interactive applications. Specifically, unlike existing NeRF acceleration methods that reduce the rendering time of each viewpoint individually, we accelerate the rendering by exploiting the information overlap between multiple consecutive viewpoints. We leverage this fact to reduce the 3D sample queries in raymarching to speed up expensive volume rendering steps. And we cooperate with an efficient neural renderer to fuse information from consecutive frames to preserve visual fidelity. Specifically, we propose a framework comprising three main components: a rendering buffer, neural feature fields, and a lightweight 2D neural renderer. The rendering buffer saves low-resolution feature maps and depth maps of previous viewpoints. From the current viewpoint, the sampling range could be narrowed by coarse proxy geometry via depth information in rendering buffer. Then, we render a low-resolution feature map and depth map at a target viewpoint via volume rendering. Next, we combine preceding and current feature maps to recover the image at the target resolution using a 2D neural renderer, a 2D convolutional neural network. The neural feature fields and the 2D neural renderer are trained jointly end-to-end and supervised by randomly cropped image patches. And we leverage the distillation from pre-trained NeRF model for better novel view generalization. The combination of low-resolution volume rendering and high-resolution neural rendering leads to fast rendering, yet maintains high fidelity and temporal consistency at a low memory cost. Here, we present corresponding qualitative results on NeRF synthetic datasets. We demonstrate that our methods can faithfully recover high-frequency texture and thin structure. We also present corresponding qualitative results on tanks and temples datasets. We present quantitative results on both tanks and temples datasets and NeRF synthetic datasets. With such a trade-off between memory usage and rendering efficiency, our method remains similar visual quality with baseline methods. And we achieved a rendering acceleration of 2 to 6 times, compared to our base implementation. In conclusion, we propose a new perspective for NeRF rendering acceleration by considering the smooth viewpoint trajectory during interactions. The combination of low-resolution volume rendering and high-resolution neural rendering in our framework leads to fast rendering, yet maintains high fidelity. We achieve better speed memory trade-off, enabling 30 fps at 1080p image resolution with a low memory footprint. For more detailed information, please refer to our paper and project page. We will soon make our code publicly available. Thank you for your attention.